To the next speaker, that is Duncan Watts. He's a postdoc in Oslo, and he will talk about adding external data sets to this. So, Duncan, please go ahead and share your slides.
Hi, everyone. My name is Duncan Watts, and I'm a postdoctoral researcher here at the University of Oslo. And today I'm going to be talking about work on extending the BeyondPlanck framework to external data sets, specifically Wmap in this case. So I'll just begin with a brief background of the Wmap experiment. As we all remember, the Wmap Observatory was a 5-frequency experiment observed for approximately 9 years. The experiment was a precursor to Planck, so it has higher white noise levels. However, it's a quite robust data set in general, and it's also a good complementary data set to the Planck low frequency instrument because its frequencies essentially lie in between those of Planck LFIs. This by itself suggests that a reanalysis in the Gibbs sampling framework would be quite interesting, even just as a validation of the BeyondPlanck framework for a different data set. Beyond reproducing the BeyondPlanck results, TOD level analysis that includes both data sets would help to break degeneracies due to specific scan strategies employed by both instruments. And also, one kind of nice thing about this is that the Wmap data analysis has been well documented by the Wmap team in the explanatory supplement. So reproducing the raw time-ordered data analysis is a relatively straightforward task. So with all that said, it would be interesting to reanalyze the Wmap data starting with the K-band. So as, sorry, my slides are not progressing. Okay, didn't mean to include all that at once, but K-band would be a good place to start, essentially because its map at 23 gigahertz is the best publicly available template for polarized synchrotron emission. So if we had an updated analysis of this data, it would be unquestionably very useful for future analyses. In addition, the time-ordered data themselves are very well understood. And the data set itself is very low volume. So it's about 626 gigabytes for the entire Wmap data set, and about 80 gigabytes on disk for the K-band alone. So this is a volume that's really not difficult to process on a small cluster like the one at University of Oslo. And so on the last point alone, just being able to handle the data volume, that would improve the Wmap analysis without modifying the algorithmic pipeline at all. When the Wmap data was first processed, it was only performed 1 year at a time, partially for systematic, for good handling of systematic properties and the time sensitivity over the course of the instrument, but also because it was difficult at the time to just load in all of that data, so they didn't do it. Including all of the data at once would be a statistically robust, and it would improve the Wmap data set just sort of for free, which we can basically do with now. One more, I think it's worth talking about the observing strategy for a moment. So for one thing, the Wmap data it's inherently differential. It has 2 horns that are pointing at approximately 141 degrees away from each other, and the detectors record the difference in intensity between the 2 directions. And so this is a kind of unique strategy, and in one of the things that gets you is large fractions of the sky that are covered in short periods of time. Additionally, this allows for, there's a lot of pixel crossings over the course of the experiment. So pixels are reobserved several times at different orientations, which allows for a robust characterization of the polarization of the sky and instrumental effects. So with that said, the actual Wmap data model is a little bit different than most other experiments. So it's organized into differencing assemblies per band, where differencing assembly has basically 4 data streams, 2 of which are sensitive to orthogonal polarizations. So if you subtract one polarization, one detector stream from another, you become polarization sensitive. And so the data set explicitly can be written down like this, where the raw time order data given by C is given by this time-dependent gain factor, like most instruments, and then the pointing for each horn with a -1 to the ith power corresponding to the different polarization orientation. And there's this extra alpha parameter, which includes the difference in the, what's the word for this? Essentially this is where the imbalance comes from. Basically, the reception of each horn to the polarization is slightly different for horns A and B, and that needs to be taken into account and actually fitted during the time-ordered analysis. I also just want to point out explicitly that the gain and the baseline here, the G and B factor, were fit to the time order to the solar, no, sorry, fitted to the orbital dipole, and the baselines were fitted once per hour, which is inherently a little different from how the BeyondPlanck analysis works. I'd also like to talk about how this changes the processing of the data. So for an idealized single horn radiometer, you'd have a pointing matrix that's just given by ones and zeros, and the map making matrix, P transpose and inverse P, will be diagonal. This means that when you do map making, you don't need to take into account other pixels. So you can essentially process the data set one chunk at a time, and you never actually need to load in all of the data at once. However, for differential pointing, the pointing matrix ends up having both positive and negative ones, even for just temperature, which basically means that the mapping matrix, P transpose and inverse P, has off-diagonal elements. This is no longer a matrix that can be solved one pixel at a time, meaning that the entire data set needs to be loaded in all at once in order to invert it and solve the map-making equation. And we can do this again using the conjugate gradient iterative matrix inversion method, which is what the Wmap team did for their analysis. And at this point, holding the entire data set in memory becomes a requirement rather than a speed concern. So this is specifically the point where the Wmap analysis could have gone a little bit further, and which we will hopefully just improve just by reproducing. One other improvement that we plan on making to this pipeline is taking advantage of the discretized nature of the data set. So the raw uncalibrated data are stored as 5-digit floats, but they can easily be represented as approximately 50 different integers, which are much less data intensive. As Matthew talked about, this is being implemented for LFI already, but when it's going to be implemented for Wmap, it'll be an even larger data volume reduction on the order of about factor of 5. I also want to point out that we have changed the analysis pipeline slightly in that we're not explicitly doing baseline and gain fitting as separate steps, but using the noise and gain sampling that Eirik and Håvard described in their earlier talks. And with that, and with the caveat that this is very much a work in progress, here are the current results as they stand. So to begin with, I'd like to show the commander processed Wmap data. And at this level, there's very few defects in the map that are easy to see. And probably the interesting thing would be to see what is the difference between this and what the Wmap team produced. And so when you take the difference between the two, the most obvious thing here is the solar dipole. And this isn't really fair because the solar dipole was removed during the Wmap time-ordered processing. So from here, it would make more sense to remove the solar dipole. And once you do that, you can see that there are some differences in the processing method that are a little bit more clear. Off the plane, there's pretty good agreement, but there are clearly some issues remaining, including the point source processing and the residuals along the galactic plane. You can see this sort of X structure here. I will say, though, this is an incomplete solution, and we haven't yet included all the commander machinery in the solution. But I'll just say for now, we've got more work to do, but we are well on our way, and this is pretty exciting. As for how expensive this is, just want to give some quick numbers. Basically, the data volume is modest, requiring about 170 gigabytes of RAM, takes about 3 minutes to initialize, and the map making process itself takes about 800 seconds to converge using one node at the University of Oslo cluster. And to close up, I'll just say that the the current analysis took as fixed the Wmap instrument parameters, including the radiometer model and the Horn imbalance parameters. And some of these can't be improved using just the Wmap data alone, basically due to the scan strategy. However, in combination with Planck, these degeneracies can be broken. One specific example is this map of the quote-unquote poorly measured modes, which are polarization patterns that were projected out of the Wmap dataset because they were excited due to uncertainties in the imbalance parameters, these alphas that I mentioned before. Now, so basically, just because of how the mapping strategy worked, you can't get patterns that look like this in the sky, and they're just projected out of the final solution. So with the joint analysis, these modes can effectively be recovered and allow for a more robust understanding of the large angular scale fluctuations measured by Wmap. And so, of course, none of this work would be possible without the European Union funding. So thank you very much to the EU for recognizing the importance of this work and enabling it to be performed. And with that, I will be happy to take any questions. Thank you.
Thank you, Duncan.